Welcome back to the next session where we'll have 4 talks on randomness generation. Okay, I think the title was somehow there was a mistake in the title. Sorry about that. I think that it was called randomness future or future trends or emerging trends in random generation. All right, so the first talk will be given by Pratik Sarkar from our own Super Research. Pratik, can you please share your slide?
Yeah. Can you hear me?
Perfect.
Should I start?
Sure. So let me just say that Pratik will be talking about InstaRand, our recent work. It's a joint work with Jacob, Aniket, myself, Lucian, and Arvind. I think at the start. Okay. Yeah.
Hello, everyone. Today I'm going to talk about InstaRand. So this is a joint work with Jacob, Aniket, Pratik, and our collaborators from CISPA and University of Sydney, that is Lucian and Arvind. So before going into InstaRand, let me talk about the various applications of randomness on the blockchain. So as we have seen in yesterday's panel discussion, we need randomness to play on-chain poker, say on-chain lottery, or you can also use randomness to craft NFTs in your favorite game. Now, the question is, how do you define this good randomness? What is the property that you need from these random values? Firstly, they should be unbiasable. That is, no one should be able to bias the value of the randomness. Secondly, it should be unpredictable. So no one should be able to predict what is going to be the future random value. Otherwise, suppose you are playing an on-chain lottery and you get to know what is a winning ticket number. Then you can always win the lottery. So it breaks the whole purpose of lottery. And thirdly, there should be a mechanism to verify that the randomness was correctly generated. So this is public verifiability. So Jacob talked about these properties in details in yesterday's talk. So now the question is, how do we use smart contracts to generate this good randomness? Because all these applications that I mentioned, they use smart contracts. So our first approach is to use a classic cryptographic primitive called PRF or pseudo-random functions. So here, given a random short secret key, SK, you can generate, the smart contract can generate an output Y by running the PRF function on this input X using the hidden secret key SK. Now the PRF security ensures that this output Y is indistinguishable from a random string, assuming the SK is hidden. So this is a classic way to generate randomness. However, there's a problem. Smart contracts cannot store secret keys on chain because the states are public. So there's another way to do using private smart contracts, but we will not go into that. We will assume public smart contracts. So here SK cannot be stored. So how do we solve this? So we rely on this technique called off-chain computation, where you delegate the computation of Y to an off-chain node or off-chain service, or in this case, it will be Supra, or even Chainlink, or say Algorand or Aptos. So they will maintain the secret key within themselves, right? And they will compute the output Y on an input X using the secret key, and they will produce a proof pi that Y is correct. So this is called off-chain computation. Now, let me redefine the primitive or redefine the primitive of PRF in this setting. So in this setting, the PRF primitive becomes a VRF. So here, again, we repeat the same process. That is, Y is computed on X. But in addition, there will be a proof. So let me tell you what are the properties of VRF needs to satisfy. First, it needs to be unbiasable. That is, the output Y cannot be biased. Secondly, no one should be able to predict Y on a given X without the secret key escape. And thirdly, this is an additional property called public verifiability. That is, the key owner can produce a proof pi so that anyone can verify that Y was indeed correctly generated corresponding to this input X. So this is the additional property of a VRF on top of PRF. Now, using the primitive of VRF, let me show you how existing VRF services work. So this is the simplified version of how Chainlink or Supra works. So here there is an user on the left. So the user wants to get a random value on its input X. So it first queries the VRF smart contract on input X. to obtain, and the VRF smart contract generates a input INP, and this is corresponding to input X, and this is forwarded to the off-chain node or the off-chain VRF service. And this VRF service has already sampled VK and posted it on-chain previously, everyone knows it. And this secret key SK is private to it. And now on being queried on this INP, the VRF service will generate this output Y in a straightforward way, and it will also compute a proof. And this output Y and proof is sent back to the smart contract. The smart contract verifies the proof pi and appends this input Y on the blockchain, and then forwards the output and the proof to the user. So this is how a VRF service works. Now, a problem over here is if the user wants to obtain multiple random values, then it has to query the VRF multiple times. For each Y1, Y2, Y3, it has to query with X1, X2, X3. So this brings to the next question. Like each Y necessitates a request to the service. Now, suppose you need n different randomnesses. So this will require n different requests to the service. So let me show you an example of how this is a problem. Suppose there's a user who wants to play a snake and ladder game. And we know it's known that an average snake and ladder game requires 48 dice rolls. So now in each round or for each die, the user is going to query the VRF service with the input dice 1. And this is going to be forwarded to the VRF service. The VRF service is going to respond with the die value, which is Y1 and the proof pi1. And this will be repeated serially. So for each die roll, the user has to query the VRF service 48 times. Because you want the first die to be valid, only then you will proceed to the second one and third one, and so on. So this is very expensive because you have to incur the server latency for 48 queries. And also you need to incur the gas cost of verifying all this 48 proofs. And concretely, this turns out to be like almost a $15 cost in terms of gas cost. And it requires 48 queries to the VRF service. So the question over here is, can the user pre-compute the VRF output? Like all the computation that is performed or the VRF request that is made by the client to the server, can it be pre-computed so that the online latency will be small? And also, can the client or the user reuse the output so that it does not need to pay the cost every time? So to partially address this question, the work of FlexiRand was introduced by the Supra team last year. So they introduced this primitive called output private DVRF or output private distributed VRF. So let me show you how an output private distributed VRF works. So it is almost similar as a VRF service, except the VRF node on the right-hand part will be distributed. That is, it is run by a bunch of servers instead of a single server. And the output privacy boils from the fact that the user will now blind its input, and this is forwarded to the smart contract. So, and the smart contract verifies the blinded input, and this is forwarded to the VRF service. And the VRF service will compute a blinded version of the output and also a blinded version of the proof. And this will be forwarded to the smart contract and sent to the user. So this happens in the pre-computation phase. So here, only the user will know what is Y and pi. The DVRF service or the smart contract or no one else will know what is this Y and pi. And in the online phase, when the user wants to use this Y, it will unblind this Y or unmask this Y and the corresponding pi. So in the online phase, it will not incur this client server latency and it will also not incur the gas cost of this computation. So this is how an output private DVRF works. And as you can see here, this supports pre-computation because the entire VRF computation is performed in the pre-computation phase. Say you can perform this VRF protocol at midnight, and in the morning when you want to play some game, in the online phase, you will just unblind the output and use it. So this supports pre-computation. Now, what about reusing the output? So in the previous, like in the output private DVRF, as you can see that the client can reuse this output Y to generate multiple outputs using a hash function H. So this hash function is modeled as a random oracle. So how does it work? So the user can compute multiple random values as Z1, which is hash of 1, y, z2, which is hash of 2, y, and so on. So it is deterministic given the output y, right? And now to verify each zi value, the corresponding y and pi value has to be made public. So in FlexiRand, this is a limitation that you cannot verify each zi value individually. You have to verify all the z values together, because when you want to verify z1, you have to make y and pi public. And this will leak the z2, z3, and the future zn values, right? So as a result, all the z values have to be verified together. And so the outputs are not instantly verifiable. And this is a problem in protocols or in games where you want each random output of a round to be independently verified. So the y cannot be fully reused, right? Because here it's partially being reused. So this brings us to the question, can the extended outputs be instantly verified? Like, can we instantly verify the y's without leaking? Can we instantly verify the z values without leaking the future z values, right? So you want to verify and use z1 irrespective of what z2 will be. And then you want to use and verify z2, and then again z3 and z4 and so on. So this is what we call instant verifiability. So before going into our result, let me briefly talk about the current existing works in the literature. So here, let me first talk about the VRF services offered by Chainlink and Supra. So here the output cannot be pre-computed. So whenever you need an output, you need to query the user needs to query the VRF service and obtain the output. This is because there's no output privacy. And similarly, output cannot be reused because there's no output privacy. And also it's not instantly available or instantly verifiable. But the VRF service can be deployed on any blockchain because it does not, like the VRF service does not rely on the underlying blockchain protocol where it works. Next, we have FlexiRand, which we discussed. So here you can pre-compute the output and partially reuse it, but you cannot instantly verify the output. So that's why there's a cross mark over here. However, FlexiRand can be deployed on any blockchain as it is same as the VRF services. And there's a recent concurrent work by the Aptos team. So this is called Aptos role. So here the output cannot be pre-computed or reused. However, the output can be instantly obtained or instantly generated. So whenever the user wants a randomness, it queries the Aptos service, and the Aptos service will bunch up all the requests together in a block and have a consensus on it, and then apply a random beacon on it, and then generate the output from that. So the output is instantly available because the latency is very low. However, the Aptos role does not work on any blockchain because it relies on the specific blockchain property where the consensus on the block has to be done before the beacon can be generated on the block. So it's a two-phase process. So next, finally, we have InstaRand. So in InstaRand, we will show that how we can pre-compute the output, and the output can be reused. That is, you can generate the same output from the pre-computation phase to generate multiple extended outputs. And these extended outputs can be instantly verifiable, right? And we can also deploy on any blockchain. And in fact, InstaRand is not just a protocol, it is like a framework or like a compiler which can improve or which can upgrade existing beacon protocols with instant verifiability. So I'll talk about this in more details in the next slide. So this is InstaRand, instantly verifiable on-chain randomness. So what are the properties of InstaRand? So here you can pre-compute the output. So the user pre-computes one VRF output. So the user needs to query the VRF server once in the pre-computation phase. In the online phase, the user will use that one single VRF output to generate multiple outputs, okay? And each of these multiple outputs or these extended outputs can be independently verified. So that's what we call instantly verifiable. And this is blockchain compatible because the extended output can be used on any blockchain, or in fact, the InstaRand protocol can be applied on any blockchain. And finally, I will show in the technical slide that InstaRand can be applied not just on VRF service, but you can apply it on existing beacon services as well, like, for example, Algorand beacon or DRAND beacon or even the Aptos role. to provide this output reusability and instant verifiability feature. So you don't need to query the beacon again and again. You can, or use it again and again. You can just get the output once and reuse it to generate multiple outputs. So now let me show you how InstaRand works. So this is the pre-computation phase of InstaRand. This is very similar to how a plain VRF service works. So here the user will query, but there are like two changes which are highlighted in orange. So first, the user will sample a key pair, a VRF key pair, denoted as user public key and user secret key. And this user secret key will remain with the user. And now it will query the VRF service on its input X and the user public key, UPK. And then this X and UPK will be forwarded to the VRF service, will generate the output Y and the proof pi, same as before. And this will be forwarded back to the smart contract and it will be sent to the user. And this UPK is also posted on the blockchain, just to clarify, because everything is happening on the blockchain. And now this is done in the pre-computation phase. And in the online phase, the user will generate instantly verifiable outputs using this USK and this output Y. So we don't need this output Y to be private. Instead, the user will generate multiple outputs using the USK, and this Y kind of acts like a public seed or like a nonce. And just to talk about how to extend this to beacon on any randomness service. So here I have described it using a VRF service, but instead of VRF, you can assume it can be a beacon or any randomness source which provides an output Y and a proof which attests that the output Y is correctly generated. So this can be replaced using a beacon, and everything will still work. So in the InstaRand paper in this work, we only considered VRF service because we wanted to show that just using one VRF, like just using a plain VRF, you can obtain this instantly verifiable VRF. But you can also extend it to beacon plus a VRF. Now let me show you how in the online phase the user can generate multiple instantly verifiable outputs before this. So from the pre-computation phase, the verification key of the server is posted. Then the output Y, the proof pi, and the input X, and the user's public key are also posted on chain. So everyone knows this. Now to generate the first output, like the first extended output, the user will compute W1, which is the VRF computation on X, Y, and a counter 1, because it's 1. Yeah. And this is performed using its own secret key, USK. And this gives the user a proof pi 1. And the output is set as Z1, which is hash of 1, W1, X, Y. So this is a random oracle invoked on this XY1 and this W1. And then the output is set as Z1 and the proof is 1, W1 and Z1, pi 1. So basically the proof is going to be this VRF output W1 and the corresponding proof pi 1. And now if the smart contract wants to instantly verify this output, the smart contract will first verify the proof pi 1, and then it will recompute Z1 as hash of 1, W1, X, and Y. So verifying this proof verifying this proof pi 1 ensures that W1 is correctly generated. And and then Z1 can be recomputed. Now to generate the second output, the user will repeat the same process, but now it will compute W2 on X, Y, and 2 using its own again secret key USK. And the proof will be pi 2, and similarly Z2 can be computed. And this is forwarded to the smart contract. And now the smart contract can again instantly verify the second output by verifying pi 2, which verifies W2. And Z2 can be recomputed by computing the hash on 1, W2, X, and Y. Now note that verifying Z1 does not leak Z2 because of the secrecy of USK, right? Because Z2 requires the knowledge of W2, and W2 cannot be computed by anyone other than the user because USK is not known. So that's the idea. So now let me give the formal security argument, or let me argue formally like what it means. So this is like the VRF server computes Y using SK. This is performed in the pre-computation phase. This Y is computed. In the online phase, this WI and ZI is computed by the user using USK. So now to argue unbiasability, this ZI is unbiasable since this output Y is unbiasable, right? So if you look at it if you inspect it, then you can see that once the user queries the VRF service on X and UPK, everything becomes deterministic, right? This Y, so it cannot be biased. So Y is computed from X and UPK using SK, and it's random because we use a random oracle. So that's why the final output ZI is unbiasable. Now to argue unpredictability, no one but the client or the user can predict what is WI. As a result, no one can predict what is ZI. And this is because of the security of USK, because no one can compute what is WI. So this is unpredictability. So I would like to note here that the client can pre-compute once it has obtained Y, it can pre-compute what the ZI values will be. And there are additional mechanisms for it. And we can tackle that by using some off-chain query to the VRF service in the online phase. But I will not discuss that in the talk because it's a bit more complicated. And then now let me argue why each ZI value is instantly verifiable. So each ZI can be instantly verified without leaking ZK. This is because of the public verifiability of this VRF, right? So you can independently verify WI and WK without leaking each other. So that's why each of these ZI values are instantly verifiable. So now let me show you an application of InstaRand. So let me go back to the snake and ladder game. So here, suppose there are two InstaRand clients, user A and user B, who wants to play the snake and ladder game without querying the VRF service again and again in the online phase. So they will use the InstaRand protocol. So both users perform the InstaRand pre-computation with inputs XA and XB on snake ladder A-B. So in the pre-computation phase, they commit that we are going to play snake and ladder game together. So and also their public keys are posted in the pre-computation phase. So that is there. And now in the online phase, so there we have the DiceWeb smart contract, which will take input, like the extended outputs from both of these users one at a time. And then it will verify this XA and XB and these individual proofs. And for the ith round, it will generate the dice as hash of I and each of these random values, right? So to generate the first die, the smart contract will hash 1, this Z1A and Z1B, right? And that will give you the first die. And this will be repeated in sequentially multiple times to generate n die rolls for n different die rolls for n rounds in the snake and ladder game. So this is how InstaRand can be deployed to play two-player snake and ladder game. And it can also be used in other gaming applications like backgammon and Yahtzee and so on. So note that here the dice is unpredictable, like this die value will be unpredictable when one of the user is honest. Suppose user A is honest and user B is corrupt, and user B wants to predict what the die roll will be. But user B cannot do that because each of the ZI values will be unpredictable because of the unpredictability nature of InstaRand, right? The unpredictability feature of InstaRand. So that's why each die I is unpredictable when one of the user is honest. So now so there are a couple of questions. Maybe I'll take it after the talk. So now let me talk about the experimental evaluations. So in the benchmarking, as you can see, there are two VRF protocols, one on the server side and one on the client side. So on the server side VRF, we actually deploy Glow DVRF to support decentralization of the server. But you can also consider the Chainlink VRF service, or you can, in fact, even use a beacon service to instantiate the server. On the client side, we actually use the DDH VRF by Goldberg et al. So this is the one used by Chainlink. This gives us very good efficiency because this will scale in the online phase, right? So we want this client-side VRF to be very fast. Whereas this Glow DVRF, this can be slow, it relies on pairing, but it is only one time. Now coming to the pre-computation phase, the cost of the pre-computation is a single query to Glow DVRF service, and it requires 2 on-chain transactions, right? So it's just the Glow DVRF service, like one VRF query from the client to the Glow VRF service. So that's the pre-computation cost. And in the online phase, so the client will instantly generate random values ZI, and each ZI value can be generated in less than 0.2 millisecond. So that's the client generation. Like, it basically requires the generation of one exponentiation, one Schnorr proof, and one hash computation. And to verify each ZI, you just need to verify one Schnorr proof. Actually, not Schnorr proof, but I think one Schnorr-Medicine proof. Yeah. So that's why the verification of each ZI is also very fast. It's like 0.22 millisecond. Now let me talk about the gas cost comparison. So as you can observe, InstaRand generates n instantly verifiable outputs using n+2 on-chain transactions, because you need 2 transactions in the pre-computation phase, and in the online phase, the clients just send the output to the VRS smart contract. So that is 1 transaction for each output. So that's why we can generate n+2 transaction using n outputs using n+2 transactions. Whereas all the other protocols, they require at least 2n transactions. So now let me go into the graph. So here FlexiRand and Glow VRF, they are more expensive in terms of gas because they require pairing checks at the for the verification. That's why they are more expensive. However, the DDH VRF or the Chainlink VRF is the least expensive protocol over here, but they require 2n transactions. So that's why InstaRand starts outperforming Chainlink VRF or DDH VRF when you require, say, 7 or 8 outputs. So as you can see, like for 10 or 15 outputs, InstaRand starts becoming better. And this is because of the extra transaction cost incurred by DDH VRF, which involves like storing stuff on chain and so on. So this is the gas cost comparison. And finally, to summarize, we introduced the notion of instantly verifiable random function. We showed how to construct this notion of instantly verifiable random function from plain VRFs. And we also proposed like ideal functionalities in the UC framework to model this instant verifiable random function. I didn't talk about that in this talk, but yeah, it's there. And then this IVRF supports pre-computation. And finally, and also we show how this primitive generates n outputs using n+2 on-chain transactions. And finally, we can also upgrade existing randomness services such as beacons to allow instant verifiability. Yeah, thank you.
Great, right on time. So
thank you.
So actually, I answered all the questions, but I think like most questions about like input pattern and some other questions about the verifiability on chain. So it was okay. So yeah, that's good. Actually, I think we can actually move on to if there is no other question, I think we can move on to the next talk because we're pretty running slightly late. So it's good. The next talk. Thanks, Pratik.
So just one thing for people who just joined today is that if you have questions, most of the authors can still answer via chat. So you can just put the questions and they can answer it
afterwards.
Yeah. Okay, good. You can just post the question now for any of the previous talk and they can answer even now.
Yeah. All right. So let's move on. So Sriram, can you share your slide, please? But also turn on. Okay, we can see you. Can you speak?
Yep.
Okay, good. So we can see you, we can hear you. So next talk will be by Sriram, Insta Poker, real-time poker on blockchain. Sriram is a grad student at UC Berkeley, was an intern at Supra last year, and this is his internship project. So over to Sriram.
Yep. Thanks, Pratyay. Yeah, so Pratyay said this is joint work with Sanjim, Aniket, Pratyay, Rohit. And this is my internship project at Supra last year. And yeah, so this project is about how you play poker in real time on blockchain. All right, so what's the question here? The question is, how do you play poker or other card games over the internet without trusting some third party? And the reason you don't want to trust a third party is because, like a bunch of other talks that we've seen, generating randomness is something that is very important. And we need to make sure that the output is actually random. And in addition, for card games, we have certain other conditions, which is that the output must be private, in a sense that you don't want the other parties to know what cards you have. Even if you know it's a shuffled deck, you need to know that the deck is shuffled, but you should not know the other party's cards and vice versa. And we also need some public verifiability so that people looking at the game from the outside can be assured that the game has been conducted correctly. And these are some of the requirements that we actually need to care about while playing card games. And the core issue again is how do you generate correlated randomness, in the sense that how do you generate permutations? And this isn't covered exactly by, say, VRFs or verifiable random functions, because you also have to generate some correlation between the successive calls of your random function. So let's look at some existing solutions. So one possible solution that is currently implemented is players take turns shuffling cards when they arrive. So when the players decide to start a game, each player shuffles a deck, proves that they've generated correctly, and pass it on. Of course, these are done over encrypted cards, so the players do not actually leak the shuffle. And this is a protocol that works, and it only requires one of the players to be honest to ensure that the final shuffle is random. However, there is an issue that you need to wait for all the players to do it. The game doesn't start instantly, and the proofs are also not necessarily easy to compute. And the players may be lightweight machines, maybe just mobile phones, so this might not be fast either. And yeah, these are some of the issues. So the shuffling is done in the online phase, where the players actually generate the permutation online. And we also have failure modes where some of the players might drop off, and then the other players have to decide, what do we do? Do we stop the protocol? Do we start again? And we also have issues of proof computation, which is expensive because the players could be lightweight devices. And we seek to solve these questions by offloading a lot of these problems to the offline phase where more powerful servers can do it. So what do we try to do? We try to generate offline shuffles, in the sense that we generate permutations that are offline, and we still need to prove that they're correct. So we produce publicly verifiable proofs that the shuffles are correct, and such that when the players arrive to the game, they can start playing instantly with shuffles. And just some performance numbers: to generate a shuffle of a single deck of cards, say 52 cards, and a proof of correctness, this takes about 3 seconds. And notably, this can be done offline. So this can be done before the players even arrive, or even before the players are known to the protocol. And the player time, which is the 0.4, is all they need to do is verify a proof, pick their cards, and start playing, which takes around 300 milliseconds. And these numbers will be improved soon, but these are the correct numbers. And this is great because this is as close to instant as you can hope, in a sense that when players arrive, they can pretty much just verify the proof and start playing within about a second, or as long as the blockchain latency allows them to. So let me quickly monitor the chat to see if there's anything. No. So a quick primer on APC, because this is what we'll be doing. This sort of decentralized architecture is required because you don't want to rely on a centralized server doing all the computation, because we work in the threat model where we do not want to assume that there is no collusion between the server and some players, in which case, if the server knows the permutation, it can simply leak the entire deck to the player, which breaks the entire game. So a quick primer on APC is you have multiple parties with some potentially private inputs, and they want to compute a joint function on all their inputs. And we can have multiple trust assumptions. So we have honest and dishonest majority. And each of these have different trade-offs, different properties that you can get for protocols. A quick introduction to secret sharing is we use additive secret sharing, in the sense that each party has some element xi, such that a shared secret is the summation of all their individual secrets. So this in particular is useful for dishonest majority protocols, where we can say that unless all the parties come together, they will not be able to reconstruct the secret. And even n-1 out of n parties cannot figure out what the final secret x is, because they are missing a single xi. And this is being done, all of these values are being done, all these computations are being done over a field. So what's our protocol setting like? So we have two sets of disjoint servers. These servers do not interact with each other. These servers do not need to interact with each other. And they have different trust assumptions as well. So we have a set of servers called MPC servers, and where we only assume dishonest majority. So we're fine with even a single server being honest. And these servers are the servers that generate the verifiable shuffle, and they can be running in the background most of the time. They don't need to care about when the game starts. They can just run in the background, generate shuffles, and eventually when the players come, they can use the shuffles. And we need another set of servers called key servers, which actually interact with the parties with the players and provide decryption keys when they need it at game time, so they can actually get their cards. And we have one set of players, of course. The players only are known at game time because they join when they want to play, and they want to start playing as soon as possible. So this is the basic setting of what our protocol is going to be built in. And here's the roadmap that I'll come back to over the rest of the talk and talk about each of these phases. So we have 4 phases, 2 offline phases and pretty much just 1 online phase, even though it's splitting into 2 parts. So the offline phase, the empathy servers generate a random shuffle. And this has to be a distributed random shuffle, because if one server by itself knows the entire shuffle, then if it's dishonest, it can simply collude with the player and the player knows the shuffle, which breaks the entire game. In step 1, MPC servers generate the random shuffle. Then they encrypt the cards and produce a proof that it actually corresponds to a valid permutation. And this is important because if the servers are malicious, they could potentially cheat and you'd get something that is not a valid permutation. And in that case, the game is not a valid game at that point. And the online phase is the shortest phase in our protocol, where we want to say at game time, when the players know, they get the decryption keys from the key servers, and then they verify the proof, get their card, and they're good to go. So let's look at part 1. How do you generate the random shuffle? So at the core of it, the question is, how do you generate a random permutation of some set of values, let's say 1 to 52, such that no server knows what the permutation is? Here, this is a functionality where the input is empty because we just need to generate a random permutation. There is no input to this functionality. And at the end of it, we want each server to end up with additive shares of the permuted values. Let's start the warm-up protocol. How do you generate shares of a random value in some small space? We're not asking how do you generate the entire permutation, but just for a single random value. So concretely, what we want is that each server should get some xi, such that when reconstructed, that is when you take the summation of all the xi's over all servers, you get some small random output in some small set. Let's ask an even simpler question. How do you generate random bits? It's so where C is of size 2, or the set of C is size 2. So here we have this protocol that can generate random bits. So the parties first sample a random sharing of some element. So each party just chooses a random xi. And this implies that when you add all the xi's together, you're just going to get a random value. This is not restricted to a small range. So in step 2, the parties commute x square, which is still a random number in the field, sorry. And they reconstruct it to get x square. So now that x square does leak information about x. In particular, that when you get x squared in the clear, x can be one of 2 values. And we use that crucially here in the next step, where we compute square root of y, which is a fixed root of x squared, and multiply to the share of x. Sorry, this should be inverse of square root of y. Yeah, it's y to the power minus half. And this is going to be a share of plus or minus 1 with equal probability. And this is because each square has 2 square roots over a field, and you're going to get one of the square roots with high probability. You're going to get one of the square roots with probability 1. So what you actually get is a share of plus or minus 1. And it's easy to convert these shares of plus or minus 1 to a random bit to get 0 or 1. Just add 1 and divide by 2. The core idea of why this protocol works is because of this property that the map x to x squared is a 2 to 1 function over the field. And this property holds for all fields that are such that the prime is 1 modulo 2, which holds for all odd primes, which is fine. And how do you extend this to general ranges? In general, for small ranges, of course, is parties can sample random sharings, and instead of x squared, they now compute x to the power b instead. And then they can reconstruct to get y equal to x power b, and the parties then locally compute an output y to the b inverse times x. And this gives you a share of a random root of unity. And this is not just a plus or minus 1, but instead you get a set of size, well, whatever the order of the root of unity is. And for this, you need a b to 1 property instead of a 2 to 1 property, which requires that p is 1 more b. So now that this is a stronger condition than what we had before. For instance, if you want b equal to 52, then your prime field must satisfy p is 1 more 52, which is not necessarily true for most fields, but it turns out to be true for b into 56. Now that we have some way to generate small random values, how do you build a permutation from these? So one sort of naive way to do it is you can generate a lot of random values, get a whole stream of random values, and you can pick the first b unique random numbers. And this will be a random permutation. For instance, look at the stream where we can discard all the repeat elements, which are all in red. And you keep running the stream until you get enough elements in the range. For instance, here the range is 6. And this gives you a permutation of size 6. It's random as well, because all the numbers are random. However, this cannot be used directly in our protocol because we have shared values. None of the parties actually know what numbers they generate are. So how do you check if two distributed or shared numbers are the same? So we use distributed PRFs, and suppose we particularly use this PRF called the Rhodesi-Apolsky PRF, which is g to the power 1 by x plus k, where x is the input of the PRF, k is some key. And how do you use this to check if two numbers are the same, to shared values? So you can compute the PRF and reconstruct it on any shared input. And this gives you the valid PRF output. And note that if the input is the same, the PRF output will be the same because it is deterministic. So once you compute the PRFs and reconstruct, you can keep the shares corresponding to the first be unique PRF evaluations instead of looking at the unique numbers itself. And why is this better than what we had before? It's better because now the input is not leaked. So pseudo-randomness actually hides the input. And we can actually construct the permutation from the random values. And note that because the key is distributed as well, no server can compute the PRF by itself, so it cannot brute force and figure out what inputs are just by looking at the PRF itself. Now there's another question of the property that I mentioned before, which is P is 1 mod B, is restrictive. And it turns out for most elliptic curve groups that we're working with in practice, they're highly two-adic, and which implies that P is usually 1 or P minus 1 is divisible by a large power of 2. Which makes the condition P equal to 1 mod 64 true for almost every group that we can look at. And hence, it's easier in practice to generate permutations of size powers of 2, but we only need 52 cards. So in this case, we can explicitly compute the PRS for the rest of the cards and discard those cards from permutation. This, of course, adds a few extra rounds, but now we can support arbitrary ranges, which are relatively small in constant number of rounds. The first part of the talk is done, where we've talked about how the MPC servers generate the random shuffle. And given this, now how do the MPC servers encrypt the cards and produce a proof that it corresponds to something valid? So typically you would assume that MPC servers can encrypt the cards corresponding to the user's public key. However, because we are doing it in the offline phase, the users don't exist just yet, the players, and the player's public keys are not known. So at this point, you cannot encrypt the public keys, so we have to use a different kind of encryption scheme. And we use identity-based encryption because we can now set the IDs to be different. So IBEs are designed in a way that you can encrypt with respect to ID versus actually a public key, and you can generate secret keys with respect to the ID. So we generate an ID as just the game ID and the card index. So whenever a player requires a certain card, they just need to figure out which game they're playing as well as the index of the card they need. And then they can request a secret key for that specific card. So this is one of the crucial steps that ensures that we can actually do our protocol in the offline phase and produce encryptions. Using a public key encryption scheme would not work because of the reason I just stated, in that you would have to know the players in advance, which cannot be done in the offline phase. Also note that this is not quite the exact Bonnet-Franklin IBE that is being used here. We still have to do some exponentiated version of it. And this is required because we need to compute all of these operations in a shared setting, where each of the servers only have shares of all the input values, and they have to compute joint ciphertext. And this can only be done with some homomorphic properties, which can be done when the encryption scheme is exponentiated, but not in other cases. So now the question is, how do you prove it? So the MPC servers generate ciphertext, but these might be malicious. For instance, the plain text might not be a permutation, and ciphertext might not even be well formed, in the sense that they don't decrypt to something that makes sense. So we can use a permutation check protocol, which is done in Plonk. And this shows that a vector is a permutation of a different vector. However, this is not enough because Plonk works with polynomial commitments, not with IBE encryptions. And as a necessary fact, IBE encryptions are not succinct. So you need a different encryption for each card. This is not true for polynomial commitments because they're actually succinct. You can commit to an entire vector in a single commitment. However, with IBE encryptions, this is not true. So what we build is a primitive called SVME, succinctly verifiable multi-identity based encryption, which does two things. One, it produces a commitment to the permitted values and converts encryption to commitment and shows consistency with the encryption values. And once that is done, we can then use Splonk's permutation check and slightly optimize, because we just need to show that it's a permutation of a public vector, not a private vector. And know that all of this has to be done in the distributed setting as well. So we need to ensure that all our protocols are homomorphic and distributable. And in the case of Splonk, this can be done using the collaborative SNORCS work that was presented a few years back. So we're done with the offline phase. And in the online phase, we have really just one step. This will be the shortest slide pretty much. And in this online instant phase, step 0 is done at some point in the past. Servers have done their part, they produced permutation, they produced a proof, and have exited. And when the players arrive for the game, they need to figure out which cards they need to get, say in indices 1 to 5 for the first player and so on. And then they can ask the key servers for the IB decryption keys. And the key servers can then generate the decryption keys based on the fact that the game ID is specific thing as well as the card ID is specific. And once they get the keys, they can decrypt the cards and verify the proof. And then they start playing. And as mentioned before, this takes about 300 milliseconds. And this is as close to instant as you can get. And some good properties here are that there's no interaction between the MPC and key servers, so these can be completely separate sets of servers. The MPC servers can also just be ephemeral in some sense. They can just quickly generate the shuffle and then just leave. And we also have honest majority for the key servers, which ensures that we actually have liveness, in the sense that there cannot be delays because of the key servers being malicious. So some experiments that we run with different number of MPC servers, and this is just showing the offline time, sorry. And here we have different size of shuffles, say 64 if you want different decks of cards. Although these are generated for powers of 2, you can generate the shuffles for any arbitrary range. And the player time here is the online time, which is less than 300 milliseconds for size 6, about 450 milliseconds for 128, and so on. And they know that these are independent of how many servers we actually use in the MPC. So we can scale up the parties in the MPC depending on the trust assumption that we want to make. And this doesn't affect the player time. And here's a breakdown of what each part of the protocol costs. And know that here we're including the Beaver triple generation, which is required for multiplication. And this is done because usually we offload these things to the pre-computation phase or pre-processing phase. But however, notice that our entire protocol is done in the pre-processing phase because it's an entire offline protocol. So we do have to include it. However, it's not very expensive because the number of cards is small and we aren't doing too many multiplications. So, yep, thanks. I can take questions now.
I think we are pretty good with time, so we have quite a bit of time to discuss on the questions. We have been already discussing some questions, mostly posed by Alan on the chat. So I see one question from Don Weaver in the Q&A.
Yeah.
So awesome method. Thanks for that. Is there a GitHub behind these benchmarks? Yes, we do have, right?
Yeah, we do have a GitHub. I think it's also, I think it's public. If not, I can share the link in chat.
Yeah, I mean, you can just take your time and can answer this question. Any other question? Okay, Alan has another question. Sriram, maybe you can take that. Q3, for online poker, no matter what cryptographic protocol one is there a fundamental problem one can add fake players to an in-player poker game and gain an advantage, unless it's a two-player game. Okay, you want to answer that or?
I don't know if I have a good answer to that.
Maybe I can try.
Yeah, sure. Go ahead.
Yeah, so the idea is indeed the problem you're talking about. People say like all the typical rules where the host is not a problem, but players themselves are sitting in same room showing each other cards, or same parties playing two different rules. So indeed, this is not the concern here that is addressed. And those problems are interesting by themselves, but I think the game industry is already working on that in terms of how to demonstrate those aspects to that people. You're not sitting and showing cards to each other and stuff like that. But they are indeed non-cryptographic problems. And the way we understand it, actually, there is some work towards that. the major completely unanswered questions were precisely that what if the host just decides and play maliciously and gives out the cards or tell the cards to each other and stuff like that.
Exactly. Also, Rohit said this, I guess, the same thing. Like it's the same problem exists in the Web2 poker as well. So nothing that we introduce here. Like Rohit, you want to add something? I think you can speak up. If you want.
Hello, can you hear me?
Yes, yes.
Yeah, I think this is an interesting point because our protocol reveals what are all the players that are on the same hand, which perhaps online poker sets don't. So I think it might be interesting to look at extensions of the protocol, where I don't know, it hides who are all the different players participating in the same hand. Yeah, it's an interesting point.
All right. So if there is no other question, and Sriram, I think you can just answer to Don's question in the Q&A.
Yep.
With that, I think we can move on to our next talk. Thanks, Sriram. So the next talk will be by Jia, I think. Jia Liu. Jia, if you're there, can you just
Yeah, I'm gonna
share?
share my screen.
Okay, that's great. Sounds good.
Can you see my slides?
Yes. Perfect. Yeah. Okay. Now it's fine. All right. This is a talk by Jia Liu from Enya Labs, and she's gonna talk about zkRand, which is first non-interactive distributed verifiable random function with Ethereum compatibility. Jia, over to you.
Thank you. So I'm gonna talk about the zkRand. zkRand is a non-interactive distributed verifiable random function. It's constructed using threshold crypto, zk snacks, and PRS signature. We implemented the protocol, and the implementation is compatible with Ethereum and Ethereum blockchains. So distributed verifiable random function is a T out of n threshold crypto scheme. It enables a group of n participants to jointly compute a public random. The random output is designed to achieve public verifiability, pseudo randomness, and uniqueness. Publicly verifiable means these are the main security goals for the DYFs. Publicly verifiable means anyone can verify a crypto proof to guarantee the random output is computed correctly, computed in the expected way. So we don't have to trust any central party, central authority. We can just verify the proofs. Pseudo randomness guarantees the distribution of the random output V is indistinguishable from a uniform random from the attacker's point of view. So no one can predict the value of V before it's generated, and no one can manipulate the generation process to choose a value to give itself some kind of advantage. Uniqueness means the random output V is deterministic. It's a unique value for each public input string X. So we generate the random output on the public input string X. This public input string could be a counter, it could be a timestamp. It just needs to be a unique value throughout the protocol. Uniqueness is crucial for applications like selecting the next block proposal, the next set of validators in a consensus protocol. Because if we have, for example, if we have two output value V1 and V2, which are both valid for a given public input X, then this will give us two block proposal, two different block proposal, and two different set of validators, which will lead to a fork. This is not something we want for consensus. Also, uniqueness can help provide resistance to the block reorganization when we deploy the protocol on-chain. We need to choose the value of the public input to be independent of the block information, to be deterministic, so the generation of the random output won't be affected by the block reorganization. So DYRF is only one way to build a distributed randomness beacon. Of course, there are other approaches. Each approach has its own pros and cons. For example, the classic commit and reveal is biasable. as some participants might refuse to reveal what they have committed in the first phase if they think the current output already gives them some kind of advantage. Verifiable delay function relies on expensive hardware to establish the ASIC to establish a fast baseline, as there is a significant amount of computation for recovering the random output. So our zkRand protocol is constructed using building blocks, including the secret sharings, zk snarks, and BIS signatures. The idea is very simple. It's an improvement based on one of our previous construction for the distributed verifiable random function called GLOW. In the previous construction, we use interactive distributed key generation as the key setup. It involves several rounds of communications, so this is difficult to implement in practice. It needs synchronization among the N participants. Also, when things go wrong, when some data is invalid, it needs to settle the dispute. So in zkRand, we use snarks to make this DKG process non-interactive. Non-interactive means each participant only generates and sends one message independently without using other participants' outputs. The validity of the data is guaranteed using the snark proof. Everyone can verify the snark proof. It's publicly verifiable. If the proof is invalid, we just throw away the data. We don't need any dispute resolution process. We provide an optimized implementation in Halo 2. Halo 2 is a Planck-style zero-knowledge proof, and our implementation is compatible with the Ethereum. We implemented the protocol using Bjorn curve, and that's the only one that has the pre-compiles in EVM. So we can deploy our protocol on-chain, and Web3 applications can have access to the random outputs through Solidity contract. Let's take a look at our construction. There are mainly two components. The first one is the non-interactive DKG. The second one is the randomness generation. So the non-interactive DKG is the key setup that run among N participants. This establishes the global public parameters, including the global public key, GPK, and the verification keys for all the participants. Each participant will be able to derive a corresponding secret key that corresponds to their own verification key. And once this is set up, we can start producing the random outputs repeatedly. We can produce as many randoms as we want. To generate a random on the public input X, each participant creates a partial evaluation using the secret key they created during the DKG process. And because we have a threshold protocol T out of N, so we don't need all the N participants to generate the partial evaluations. We only need the T partial evaluations. And once we have this, we can combine them together to create the final pseudo random value. This combination process doesn't involve any secret information. It can be performed by any party. And the final pseudo random value can be is publicly verifiable. It can be verified in constant time using the global public key. So this is a high-level description of the non-interactive DKG. We have N participants here. Each one sample a private polynomial, then generate the secret shares for other participants. They also derive the public shares from the secret shares, and then encrypt the secret shares using the other participants' public key. So here we use the snarks to guarantee this computation is done correctly. And then the participant can submit this, can publish this data somewhere. For example, we could use the smart contract here to coordinate the computation to store the public parameters to verify the snark proofs. If some snark proof, like if this ZKP2 is invalid, then we can just throw away this data from the second participants. And when we have enough valid public parameters, we can combine them together to derive the global public key and the verification keys. Each participant will also be able to derive a secret key that corresponds to their verification key. This is derived from the using the encrypted secret shares from other participants. Then we can start producing randoms. Each participant generates this partial evaluation by hashing the public input string X, then apply their secret key. So this is generated on the group G1, and the verification key is also on G1. So here we generate a Shino style proof to show these two pieces of data have the same discrete logarithm. They are generated using the same secret key. And we can also submit this data on chain in the contract for verification. And when we have a T-valid partial evaluation, we can combine them together using Lagrange interpolation to compute a proof for the final pseudo-random value. So the value of pi is unique. There is only one such pi that's valid. This is the implicit, GSK is the implicit secret key that corresponds to the global public key. Then we hash pi to obtain the final pseudo-random value. So the second hash is for achieving the pseudo-randomness. That's the indistinguishability between the output and the uniform random. So we did a security analysis. We proved our protocol achieves both standard and strong pseudo-randomness. Our paper is available on ePrint. Standard pseudo-randomness is easier to prove. It doesn't allow the attacker to query the partial evaluations on the challenging inputs. Strong pseudo-randomness allows the attacker to query the challenging inputs for up to t-1 times. So this is a closer simulation of how the protocol is operated in practice. So this proved in the random oracle model under the standard security assumptions. So we use L2 with KZG commitments on the Bin curve to generate the snag proof for the DKG process. We developed the DKG circuits to compute the public shares from secret shares and to compute the encryption of the secret shares. So the public shares are generated on the Bin curve. Inside the circuits, we use the non-native encoding of Bin curve to do the computation. And we optimize the gates for computing the scalar multiplication on the fixed point generator for both G1 and G2. This reduced 70% of the gates. And the encryption of the secret shares performed on the Gromfkin curve. So we developed the gates for performing the operation on the Gromfkin curve. Because this curve can be natively encoded in the field of Bin curve, this native encoding is 25 times smaller than the non-native encoding. We also developed the solidity contract for the on-chain verification and for computation of the public parameters. We can verify the snag proofs for the public parameters, and in the contract, we can also combine the public parameters to derive the global public, to derive the verification keys and verify the global public key. And we can verify the partial evaluations and the random values. Everything is publicly verifiable, and we can check the validity in the contract. So we evaluated the performance on AWS instance. We use this machine with 32 CPU and 256 gigabytes of memory. Although we don't need this big machine for the test we have here. So the circuit degree is a parameter that determines the size of the circuit. For example, for degree 18, we can have maximally 2 to 18 gates, and the maximum number of participants we can support is 5. And when circuit degree is 19, the maximum number of participants we can have is 16. We set the threshold to be the majority of n. When n equals 5, the snag proving time is 20 seconds. The verification time is 5 milliseconds. The proof size is constant. The peak memory is the maximum memory usage during the proof generation. And this is less than 5 gigabytes when n equals 5. And when n equals 16, it's 8.8 gigabytes. So the proving time and the memory usage increases linearly with the size of n. And the verification time also increases a bit because of the size of the public instance. We didn't hash the public instance inside the circuit. So to improve the scalability and to avoid using big machines for generating the snark proof, we can divide the large number of nodes into smaller committees. Each committee will run their own DKG setup. And then for generating randoms, we can rotate among these committees based on the previous random outputs. For example, if we have 160 nodes, instead of using a circuit, we can divide this 160 nodes into 10 committees. Each committee has 16 nodes. So instead of using these circuits with degree 22 and the proving time almost 300 seconds, we can use these circuits with degree 19 and the proving time is 38 seconds. Verification is 5.4 milliseconds, and the memory usage is less than 9 gigabytes. So this can be easily computed on a modern laptop. My laptop has 32 gigabytes memory. I can run the first 3 tests on my laptop and get the similar proving time. So randomness generation is much easier. It's lightweight computation. We can compute a partial evaluation in 0.8 milliseconds. Verification is 1 millisecond. We can combine is to combine the t partial evaluations into the pseudo random value. So this this is linear of the size of t, and it's still a small amount of computation. And we never need to do this process on chain. We do this off chain. And we can submit the final pseudo random value on chain. The verification time is constant. It's 1.6 milliseconds. And we tested the gas cost for the on-chain verification of the proof. So the snark verification is expensive. But this is a typical cost for snark applications. Verify a partial evaluation costs 100k gas, and verify the final pseudo random value costs 193k gas. So part of the verification is to compute the hash-to-curve function. But we only need to compute the hash-to-curve for each public input once. So we don't need to do this repeatedly. So if we pre-compute this part, then this can save us some gas cost. And there is no pre-compile for hash-to-curve, so we have to develop it ourselves. And this part costs about 50k gas. So to further reduce the gas cost, we could use the lazy verification method. The ability to verify these proofs is crucial for decentralized application, as we need this mechanism to settle dispute without using an entrusted third party, an entrusted authority. But we don't need to verify these proofs straight away. We don't need to verify them the moment they are submitted on chain. So we could ask the data owner to put down some deposit when they submit the data, and set up a challenging period. During this challenging period, anyone can call the verification algorithm if they suspect the proof is invalid. If the verification fails, then the challenger will get rewarded, and the data owner will be punished. And if the verification succeeds, then the challenger will need to pay for the gas fee. After the challenging period, then the data owner can get whatever is left back. So this is how we could reduce the operating cost when deploying this protocol on chain. We built a demo to show how to run the zkRand protocol on chain within the Solidity contract. And also we have a simple lottery example to show how to use the random outputs. For the zkRand protocol, we have a zkRand operator, contract, and a few members here. The operator deploys the contract on chain, and each member register to the contract by submitting their member public key. These are the public keys generated on the ground keying curve. And these public keys will be used in the DKG process, and then the operator can start the DKG protocol. Each member generates their public parameters and the snark proof. The proof can be verified in the contract. The contract can derive the global public parameters and verification keys. The operator will then start the randomness generation process. by initiating the public input string X. The members can read the value of X from the contract and generate the partial evaluation and the proof and submit them back to the contract for verification. And then when we have T-valid partial evaluations, the operator can retrieve the partial evaluation from the contract, combine them together to get the final pseudo-random value and the proof. So this can be done by any party, but here we use the operator just for convenience. So the final pseudo-random value can be verified in the contract. And after that, the operator can update the value of X to repeat the randomness generation process. If X is a counter, then this is to increase the X by 1. So the lottery application, this is a very simple example. We have a few lottery users to place bets in the contract, and we use the random outputs from the zkRand contract to generate a random permutation. And the first user will be the winner and gets all the money paid by other users. So the lottery operator deploys the lottery contract to specify the public input X prime that will be used for generating the random permutation. At this point, the random output that corresponds to X prime hasn't been produced. And before the production starts, the users can enter the lottery, placing bets, transfers several Ether to the contract. And then when the random value is available in the zkRand contract, then the lottery contract can read this value and run the shuffling algorithm, generate a random permutation, and then determine the winner. The winner is the first user, and the contract pays the winner. We have the demo available here, and we have step-by-step instruction to run the demo if anyone's interested. That's all of the presentation. Thanks.
All right. So thanks a lot for your presentation. I think we're doing pretty good on time here, thanks to, I guess, like mitigated with respect the 15 minutes talk to 30 minutes. It's pretty good. So you need to average out next time. Also, we have at least one question that I can see by Aline in the chat box. Yeah, I think I had the same question in mind. Did you compare your PVS's performance to any of the following? The natural baseline of chunked Ilgamal plus range proof growths to 2021 PVSs, and we had these PVSs from class group along with Nacho and Bernardo. So can you comment on that? Yeah.
I cannot see the question here, and we had some comparison in the paper.
If you you can go to the chat,
Chat,
Yes.
meeting chat, yeah.
Right.
No, probably go down, or I don't know where.
Down, I think.
This is the last one I can see, but
Okay.
it doesn't seem to be my question.
Up. Go
Oh,
up.
that's a bit surprising. Maybe
Up. Yeah. Go up. Yeah, you have to skip the entire thread, I think.
Yeah, then you reply. Go up probably.
how come it's
Go
not
up.
there actually?
Yeah.
Yeah, because go up.
Yeah, maybe one of us can repose the question, but I wanted to ask
Yeah.
something which is closely related. Then can you go to your first performance slide? Yeah, thanks, Ari, for if you go to the first performance, where you compare the performance for I wanted to be sure that is this for NIVSS or PVSS cost, or they are for DKG that has to be multiplied, at least for the verify part, by N or T, whatever. So are
Sorry,
you
what's
comparing?
that?
This is for DKG or this is for VSS? These costs.
This is for the non-interactive DKG. This is the snag proof generation, the snag proof verification, the size.
So the reason, let's look at the verify, right? Because if you need to verify, then I think we have to perform at least T+1 verification. Right?
That was that. That's not the random generation. This is just the snag proof for the public parameters that each participant created for the DKG protocol.
Okay, maybe I'm not able to explain, but then as more PVSs are generated, this time should grow with that.
Yeah.
If it is
Like-
not for VSS, if it is for all the entire DKG.
Yeah, it
for
seems like-
yeah, the verification time grows, because of the public instance. If we can hash the public instance inside the circuits, then this will be constant, but we choose not to hash it as we cannot find the efficient hash function that can then be efficiently computed in the DKG circuits and also on the Solidity contract.
We can take that offline, and I don't think.
Yeah.
Yeah.
Yeah,
So
so it's
challenge-
not growing as much. If it's from 3 to 86, the factor should be proportional. So it's only 2 factor, which looks.
I mean,
a
even
little-
go from 3 to 9, it should grow, right?
exactly, like proportionally, because it gets. So maybe it's just. I feel like it's just the one snark verification, or maybe the snark
that's
was
what- that's
different.
what-
I don't know.
I think that's what. I
Yeah, we
felt
can
like.
take it offline. Yeah, let's see. Yeah, maybe the snark has this compression or something. I don't know exactly. But anyway, that thanks a lot, and this is quite exciting actually. And is this paper online?
Yes, we have the paper here. on
Okay.
InstaRand.
I see. It's pretty recent. Okay, should look into it. Yeah.
Yeah. So the question, Jia, is now there by Arlene. You can see, even if you can answer it, this will be relevant for you to compare, because these are different techniques towards achieving the same goal. So it can be relevant
Right.
for what you're
Different publicly verifiable secret sharing, and because it's a non-interactive, right? So state of art. I think Jia mentioned that there is comparison in the paper, right? Jia?
Yes, we compared with several
Okay,
streams in
so-
the paper. Yeah.
All right. Yeah. So I guess we can look into that. Okay. Thanks a lot. Thanks a lot for your talk. And so the final talk of this session will be by Yash. Okay. Oh, he's already sharing. Although I don't see him.
Sorry, can you see me now?
Oh, yeah. Perfect. Yeah. Here we go. Okay. So the final talk of this session will be by Yash, who is a principal scientist at Silence Lab, and Yash will be talking about verifiable randomness and threshold signing, challenge plus opportunities. Okay, over to Yash.
Yeah, thanks for that introduction. So yeah, so my talk today is not going to be about any specific result, but it's going to be a slightly different application of verifiable random functions. And specifically, it's going to be applied to threshold signing. And maybe this can be a pointer towards interesting places to develop new techniques for verifiable random functions and so on. Okay, so let's get started. The context for this talk is that cryptographic keys tend to be fairly valuable targets in practice. And if you were to store this key in any one device, that device could become a single point of failure. For instance, our friend Bob over here has secured a bunch of his assets, let's say Bitcoin, with his signing key that he stores on his laptop. If an attacker turns up, steals his key, and signs arbitrary messages to this key, she can basically drain all of his funds. And this is a bad situation. So what threshold signing aims to address is exactly this problem, which is Bob can distribute the risk of his signing key being compromised by splitting his signing key into multiple shares and storing each share on a different device, so that these devices have to collaboratively sign messages without physically reconstructing the key in any one place. So for this talk, we can consider Schnorr's signature scheme to be the running example, but really the lessons here, like the techniques here, also extend to ECDSA. So Schnorr was, I guess, designed and analyzed some time ago, but because of a patent, it was somewhat hampered in its adoption. But nowadays, we are seeing it being deployed a lot more across the internet. And it's very friendly to these kind of threshold signing or multi-party signing protocols. So as a quick reminder, Schnorr key generation happens as follows. We begin by sampling the secret key SK from the integers mod q, and exposing this key in the exponent. Specifically, the group generator G is multiplied by the signing key to produce a public key PK. And then we're assuming that we're working over some elliptic curve over here of known order. And so that's key generation, and signing the first couple of steps is the same. It begins by sampling a nonce that has the same structure as the public key and the secret key pair. And then subsequently, this sampled nonce and the signing key are combined with a sort of linear function where the weight for this linear combination is the hash of the nonce and the message that's being signed. And because we can verify linear operations with group operations in the elliptic curve, the signature is pretty easy to verify. So
The part that gets a lot of focus when we talk about Schnorr and threshold signing is the fact that the signing equation is a linear function of the key and the signing key, of the nonce and the signing key, and linear operations tend to be quite easy to distribute. For instance, if you consider additive secret sharing, where we have two devices and each device holds like an additive half of the secret, additive secret sharing is very friendly to linear operations, like many natural secret sharing schemes, where if you want to compute Z, that's a linear combination of X and Y, both the devices can just locally combine their additive shares. And so this kind of relabeling what's already on the slide, we can see that the signing equation for Schnorr is pretty easy to implement in a distributed way with additive secret sharing. Yeah, that's a solved problem. Like, how do you compute the signing equation once the nonce and the signing key have been fixed? But unfortunately, there's also this randomized step in Schnorr, which is that we have to begin by sampling this nonce every time we want to sign a message. And it turns out that the distribution of this nonce is extremely important, because if there's even a single bit of bias in sampling this value, like it should be uniform modulo Q, even a 1-bit bias can lead to a complete break of the system. There are a whole bunch of attacks that kick in with even a single bit of bias. And so to avoid relying on sampling randomness each time we sign a message for a variety of reasons, it's quite common to de-randomize Schnorr signing. Here's what deterministic Schnorr signing looks like. The signing equation is the same, like the way that the nonce and the secret key are combined is the same. But what changes is the way this K, the nonce, is sampled. And we can use a pseudo-random function instead of sampling it every time. In particular, the pseudo-random function is keyed by some long-term secret key, and it's applied to the message that's being signed to derive this nonce. And this is great. This now means that Schnorr signing is entirely deterministic, and assuming that we use a good PRF, here there's going to be no bias in the nonce. That's great, but unfortunately, this is a recurring problem that when we have to compute PRFs inside of MPC, or if we have to use PRFs in a verifiable way in MPC protocols, life becomes painful. And why do we actually care about this problem, right? The signing equation is the same, so in principle, you could just use randomized Schnorr signing in the threshold case. But for the same reasons that we use deterministic signing for the single party case, it's also interesting to look at this in the threshold case. For one, it's not trivial to get fresh, high-quality entropy every time you want to sign a message. And even using something like a stateful random number generator, which is pretty common practice, this can be a liability, especially when you're deploying applications on the cloud, where you are not completely sure if you're using fresh state every time and stuff like this. So this security issue is really the main motivation as to why deterministic threshold signing is interesting. And there's a couple of side effects. For one, randomized non-sampling is usually interactive. There are some ways to reduce this interaction if you make some stronger assumptions, like stronger interactive assumptions. But if what we care about is standard discrete log-based security and simulation security and so on, it takes a couple of rounds to sample this nonce. And so if we had the deterministic way of sampling this nonce, maybe we can save on this interaction. The other is functionality, right? That if you're willing to assume that no more than a certain threshold of nodes are compromised, then we can get now a deterministic signature from Schnorr. Right? And this can be useful for a number of things. It's useful for debugging. It's useful for checking that everything is running correctly. You can now also use deterministic signatures to see randomness elsewhere or something. Yeah, that depends on whatever application is using this. So to see why this is a challenging problem, let's look at what a naive attempt to de-randomize Schnorr signing might be like. Right, so I've written down explicitly all the details that go into realizing this like simple linear combination for Schnorr signing. The only part that's important is the first couple of steps. That's this non-sampling. And so just like plain signing, the only randomized step in distributed signing is sampling this nonce. So yeah, so while the trivial thing is to sample to have each party, like each device, sample its share of the nonce locally at random, we can think about de-randomized signing as having each of these devices maintain some long-term PRF seeds, also seed A and seed B. And now instead of sampling KA and KB uniformly where it was done for randomized signing, we can apply PRFs on the message being signed just as you would for single party signing, for each party to derive its share of the nonce. Right? So this appears to work, but here's where this fails, right? So if one of the devices, in this case, the phone, is corrupt, the problem becomes evident when the same message is signed twice. Right? So the honest party, that's the laptop, is going to derive the same nonce across both instances because the inputs to the PRF are fixed. Right? But the phone, which is corrupt, has no incentive to apply the PRF honestly. It can use a completely arbitrary value for its share of the nonce rather than applying the PRF correctly. And basically, if you trace what happens through the protocol, because the honest party's state is entirely the same across both executions, but the corrupt party's state changes, this can induce the honest party to reveal two independent linear combinations of the same secret. I haven't written down the full calculation here, but this is a well-known problem, and this is documented by Maxwell et al. From their paper a few years ago. So how can we fix this issue? That we have to really verify that the PRF evaluation is done correctly, right? That the de-randomization is done honestly. So now let's assume that both devices have a commitment to each other's PRF seeds. So when they exchange their shares of the nonces, they accompany it with a zero knowledge proof that says that the nonce that they've derived is consistent with the commitment that the other party knows. And so this basically fixes this problem. If you're able to prove in zero knowledge that you're deriving your nonces honestly, this entirely de-randomization of signing in a verifiable way. And that's all great. But now what actually goes into this proof, right? So I've written down all the values here. There's for the phone in this case, there's its long-term seed, there's a commitment to its seed, and then there's the statement that the nonce that is derived is consistent with the commitment and the seed. Right? So specifically, the statement that it has to prove is that it's applied the PRF correctly and performed an exponentiation on the PRF output. And this is essentially a VRF in the exponent, like a verifiable random function in the exponent. It's really important that we aren't proving the PRF output in the clear, but instead we are proving that the PRF output has been computed correctly, and then an exponentiation has been performed on the output. And yeah, very recently, Bonnet et al. Came up with a a nice abstraction for this problem, and like they named it an exponent PRF and so on. But yeah. So how would we actually instantiate such an object? Right? There are a few different approaches. The first that I'll cover is with the Pi-Ray encryption scheme. So with my co-authors, Claudio Orlandi and Lawrence Doyle, we had a paper last year which showed that the decryption function for A, it happens to give a very natural exponent VRF. Unfortunately, the VRF that it gives produces outputs in Zn, like integers modulo n, where n is some biprime. And then we need to do some work to translate this VRF in Zn to VRF in Zq, where Q is the curve group order. Nick, Luping, Sora, and Will also showed in their paper from a few years ago that we can use an elliptical-based PRF to implement this PRF, and then they proved that this elliptical PRF is evaluated correctly with the bulletproof. We can use any stuff, but they showed how bulletproofs are well suited to the stuff. But notice that an elliptical PRF will produce its outputs in the wrong field. Like it'll produce outputs in its base field, whereas really what we want is an output in the scalar field because it has to be a discrete logarithm value that we're generating randomly. So there are some subtleties where you have to use a different elliptic curve for the PRF than you're actually using for the signing, and there's some machinery to tie these two things together. And yeah, and finally, there's also work of mine that I had with my co-author, Guillermo Hassel and Nikolenko, where we showed that if you allow for some interaction and you're okay with the designated verifier type of setup, then you can use any standard block cipher, so as close to like single party signing as possible, and then prove that the standard block cipher was evaluated correctly with just a single garbage circuit. I don't have time to really cover all of these things, so I'll just give you a flavor of what the Pi-based PRF looks like. Right, so this is the setup from earlier. Basically, the long-term seed for the phone is going to be a decryption key for a Pi modulus, where the modulus is basically a product of 2 times P and Q. It's technically not the same modulus, and there's also a public hash function, which you can think of as a random oracle, that can map any message to a random value modulo n squared. So essentially what it's doing is that it's taking the message that's being signed and mapping it to a random Pi ciphertext. And now the nonce, like the secret value Ka, is derived by applying the decryption function on this random ciphertext. So basically, this induces a random nonce. It's secret because the output is secret because it's the output of decryption. And once we take this output modulo Q, that gives us a random nonce to use and produce this like capital RA value. And now this zero knowledge proof basically has to be a proof that this random ciphertext HFM actually encrypts the discrete logarithm of this public value array. And the difficulty here is that the plain text space for pi a is integer mod n, but the discrete logarithm of capital Array is an integer mod q. So there's some work that you have to do in this translation. In our work, we showed that there's an efficient designated verifiable proof for this that's quite succinct, and it's just, I think, half a kilobyte or something. Anyway, we have an implementation and so forth. And then Bonnie et al. Showed that there are Sigma protocols for this task, and you can compile Sigma protocols to a non-interactive proof with standard techniques to get. This is a little bit painful because the flavor of problem here that we encounter is quite similar to those that you get with range proofs and things. So you have to do either like a bitwise decomposition of the input and like prove per bit, or you have to assume some sort of trusted setup or something. In summary, this like VRF and the exponent tool can be a very useful gadget in threshold signing, or it is a very useful gadget in threshold signing for a number of reasons. And the one that I think is most interesting is this solidity state resets, and it gives you protection against bad randomness. And it can also give you deterministic multi-party signing and improved round efficiency and such. Bonnie et al. Have a good survey of this. And this is also my work that summarizes state of the art. And this can be scope for some very new interesting VRF machinery, because it seems to be quite non-trivial to solve. And with that, I'd like to conclude, and thanks for your attention.
Yeah, great. Actually, I was not aware of all these different VRF applications in the threshold signature space. I know this exponent VRF, there was this recent work, but looks like there are more out there, like Polyer-based VRF and all. We should catch up sometime to discuss more about it. However, there are a couple of questions. One from Pratik. So do you see it? What is the concrete computation cost of Polyer and custom DDH-based approach over the plain Schnorr?
Yeah, that's an unfortunate thing. It's a few orders of magnitude. If you think of a machine where Schnorr signing verification would take maybe like a fraction of a millisecond, it costs maybe, I think our implementation showed a couple 100 milliseconds or something to do this decryption and then compute the proof that you've done the decryption and proof correctly. So that was the pi 8 construction, I should be clear. For the custom elliptic curve thing, what the benchmark that I remember from that paper was on the order of a second or something to compute the bulletproof that this derivation has been done correctly. So there's a lot of scope to improve.
Yeah, I think we should probably, as a Costas has question.
Here's the one.
It's just hard to announce because it involves some notation. So Jia, you can probably
Can you see the question? Yeah.
Q&A?
It's in the Q&A.
I see. Just a second.
Or maybe Costas, you can just speak up, right?
I think if he can post on Q&A, he cannot speak up. So it's exclusive. Mutual exclusive.
Okay, so the question is that, is this tuple or not already a signature scheme? Yes, it's true. This is like the proof system itself, it's much stronger than a signature scheme. But I guess if you were okay with using any like signature scheme, if you wanted deterministic signing, you could just use BLS or something, right? So this is really relevant in settings where like you want to be compatible with some other standard that you don't have control over.
Yeah, is that all or all right then? So I think we can. So this is the end of the session, and in fact, all the talks